Hey everybody, and welcome back. Or if it's your first time here, welcome to this channel. I'm David Townsend. This is the Net Academy, where we are learning networks together. And on this video, what I'm going to go through is a continuation on the brand new series I started last week on EVPN, or Ethernet Virtual Private Network, and VXLAN, or Virtual Extensible Local Area Network Routing. Those are two big acronyms in one, and they're actually two great big topics that really work together very, very nicely. But this is part two in this overall series. In part one, what I did was actually cover the basics into what is EVPN, what is VXLAN, where are they in terms of the control plane, the data plane, what are those planes, and where does EVPN and VXLAN sit, how do they work together, and a little bit on the benefits that these two protocols actually bring. And that's actually where I want to spend this time on this video going through, is I want to spend more time talking about the benefits mostly on EVPN routing. I say mostly on EVPN routing because when it comes to VXLAN tunneling, basically the benefits of VXLAN is you are extending that layer 2 adjacency, that connectivity, that layer 2 network over an IP network. You are tunneling between different points of the network so that they feel like they're in the same geographical local area network. Really, that's the benefit of VXLAN done right there, dusted. We can move on. But EVPN is such a bigger protocol. There's a lot more to EVPN, and as such it brings more benefits to the table. Yes, it brings more complexity with it, but that's a later video. But that's why we're going to discuss what are the benefits, the many benefits around EVPN routing. Now in this video there's no lab, there's no configuration. As always, the way I like to learn is start off with the basics, build up from that, and once you understand the basics, the benefits, and all the different packet types, etc., then we can build on to the more advanced stuff, such as how to configure EVPN in a Juniper Networks environment. But as I said, there's no lab, so it doesn't matter if you're Juniper, Cisco, whoever, EVPN is a open standard protocol. So if you want to know more about the EVPN benefits, please watch this video. But enough of me talking, let's actually now just get into the benefits themselves. Okay, and the first benefit I want to talk about when it comes to EVPN, or Ethernet Virtual Private Network, are actually these two. Now I've condensed them into one big benefit because for me it makes sense to do so. So the first benefit, the first two benefits are firstly BGP, or Border Gateway Protocol, and the multi-path feature. Now if you know what BGP is, you know it stands for Border Gateway Protocol. And I cannot stress this enough, BGP is an absolutely massive protocol. There's two different types of BGP. You've got eBGP, or External Border Gateway Protocol, and you've got iBGP, or Interior Border Gateway Protocol. Really the difference I'm not going to go through here on this video, but if you want more information, just check out this link to a video I've done, or a few videos I've done on BGP. But basically what BGP does is it makes the whole internet itself actually work. It works within an autonomous system and it works outside of an autonomous system. And what BGP basically does is it advertises specific network layer reachability information, or prefixes. Prefixes being A/24, A/16, A/8, whatever it is that's inside the global internet routing table itself. Now within the network layer reachability information, you then get path attributes. Now the PAs will vary from vendor to vendor. Like in the Cisco world, you've got wait. In the Juniper world, there's no such concept as wait. But basically, the path attributes define for a network layer reachability what is the preference of a given route to actually get there. So you can actually manipulate path attributes for a particular source. If you wanted to go to a destination, it could go via this route here by manipulating specific path attributes, or by going via this route actually here. So that's really what path attributes really do, is it allows you to manipulate the routing table and the router to thus decide which route am I actually going to take to get to that given prefix, to get to that destination. But bringing it back to EVPN, with EVPN, this is of course an Ethernet virtual private network, and EVPN is basically just BGP, specifically iBGP. Now in the BGP world, you've got this address family indicator. Now when it is set in the BGP packets to 25, this is basically defining VPN. So as BGP is basically saying if the address family indicator is defined to be 25, it's a VPN. But then you've got this subsequent address family indicator, or SAFI as I call it. And this is defined to be 75 if I remember correctly, and that is defining EVPN, or Ethernet Virtual Private Network. So that in itself is just concrete details, evidence as such, that BGP is the protocol that is carrying EVPN. Obviously, we're referring to MPBGP here, multi-protocol BGP, because BGP in itself is massive. It could do a hell of a lot. It carries prefixes, it carries path attributes. It's basically what makes the internet work. And now it can actually define via this AFI and SAFI indicators that we're actually carrying EVPN as that controlling signal throughout a network inside a Ethernet virtual instance. But really, what is the big benefit when it comes to BGP here? And that is the scalability. BGP is incredibly scalable. Yes, it's very explicit. It will only do what you configure it to do, but it is scalable. It can scale from very small networks, from very small data centers, very small enterprise networks, very small service provider networks, to absolutely massive networks. And then if you add in the ability to manipulate paths via the path attributes and these import and export policies, route targets, route distinguishers, and so much more, BGP is, as I said, a very powerful protocol. But what's this multipath feature? What's this other benefit when it comes to this first part? Well, to look at the multipath, let's first look at this network here. So I didn't really cover it, and that was deliberate, but here you can see we've got 3 leaves. We've got leaf 1, leaf 2, leaf 3, and 2 spines, spine 1 and spine 2. Now each leaf has a connection to each spine. So leaf 1 is connected to spine 1, leaf 1 is also connected to spine 2, leaf 2 is connected to spine 1, it's also connected to spine 2, and guess what? It's exactly the same for leaf 3. The spines do not have any connection to one another because this is what's referred to as a spine leaf deployment. If this was a spine only deployment, there would be a connection between the spines for management purposes. But also note there's no connection between the leaves. So no leaf is directly connected to another leaf. No spine is directly connected to another spine. And this kind of looks like a collapsed core, doesn't it? In the collapsed core world, we wouldn't be talking about spines and leaves because that's more data center terminology. But here we would actually have that core, the distribution layer. And down at the bottom, we would obviously have the access layer itself, which is where those switches are really given access to all these users and all these VLANs. And the core is where you do that layer 3 routing, the handoff basically. But bringing it back to multipath, and regardless whether this be spine leaf or collapsed core with access layer switching and routing, when it comes to multipath and these different networks, what we do have in between is what's referred to as the underlay. So the underlay is a type of routing protocol such as OSPF or maybe ISIS, or in the Cisco world, definitely not covering it here on this channel, but this would be something probably like EIGRP, can't even pronounce it right these days. But basically this is where we want to establish routing on the interfaces between all these different devices. So the spine 1 builds an adjacency to all the leaves, and spine 2 builds an adjacency to all the leaves as well. And regardless of the protocol, we are actually then advertising in that loopback 0.x. So loopback 0.10.100.500, whatever it actually may be. So let's just say, for example, spine 1 has this loopback 0.1 and spine 2 has a loopback 0.2. Leaf 3 has a loopback 0.3, or I should have done something else there, but you know what I mean. Loopback 0.4, and leaf 3 has loopback 0.5. So within the underlay, so we're going to say EVPN there, but via the underlay, whether it be OSPF, ISIS, or EIGRP in the Cisco world, whatever that IGP routing protocol is, they would advertise their loopback addresses throughout that underlay itself, so that leaf 1 learns spine 1's loopback address and spine 3's loopback address, as well as leaf 2 and leaf 3. They all learn each other's loopback addressing, which has been advertised via the underlay. And then this brings on to the multipath function. Because every device has now advertised their loopback addressing, leaf 1 can see, if I want to get to the server here in leaf 1 can see, if I want to get to the server which is connected to both leaf 2 and leaf 3, it can actually see, I've got two different routes to get to that loopback 4 and that loopback 0.5 here. It can actually take this route to get to leaf 2, or it can actually take this route to get to leaf 3. Alternatively, it could actually send the packets up to spine 2 to get to leaf 3, or again up to spine 2 to get to leaf 2. So that is basically what multipath is. Multipath is using multiple paths to get to the same destination. Now the important point here is that this is only for active scenarios. Let me draw that a bit better there. Active scenarios. There we go, it looks a bit better. What I mean by that is that the server here is actually connected to both leaf 2 and up to leaf 3. And as such, leaf 1 can see that to get to the server attached to leaf 2 and leaf 3, it can do so via spine 1 and via spine 2 down to leaf 2 or leaf 3 from there. But this is for active forwarding. And you get active forwarding when you've got EVPN as that control plane. So EVPN is built on top of the underlay. It's a overlay technology. But how does user 1 actually learn, or leaf 1 I should say, how does leaf 1 actually learn that this server here is located to both leaf 2 and leaf 3? This really does come more into the packet types, the EVPN route types, I should say, for EVPN. I'm not going to go through it just yet. But what leaf 2 would basically do, and leaf 3, is they would advertise what's called a route type 1, which is the auto discovery route type. Now there's actually different types of route types 1, but basically what leaf 2 would do and leaf 3 is they would advertise over to leaf 1 via the spines a route type 1, which would define a particular ESI now, or Ethernet segment identifier. That's basically a lag for within the EVPN world. So they would build this within a lag, and that would have a particular identifier, and that identifier would then be advertised across from leaf 3 and from leaf 2 to leaf 1. And because it's the same ESI identifier, or ESI of course, leaf 1 knows that to get to this server here I can do so via leaf 2 or I can do so via leaf 3. So that's what active actually means, is leaf 1 has two paths to get to that same destination, and we're using EVPN as that overlay to get there with the underlay OSPF, whatever IGP is actually in place. And we're using EVPN route type 1 to actually advertise that ESI, that Ethernet segment identifier, which is basically in this scenario here, the lag, the link aggregation group between the server, leaf 2 and leaf 3. So that's the first two benefits of EVPN. First, built on BGP, very scalable, very powerful. And then we've got multipath, the ability to send packets to the same destination when we've got an active scenario. And in that case, those leaves, leaf 2 and leaf 3, will be using a route type 1 to tell remote leaves, hey, we've got an Ethernet segment identifier, it's the same value, it's the same ESI, and then that remote leaf knows I can get to that destination via these two separate leaves. Multipath. And moving on to the second round of benefits. And again, what I've done is I've grouped these two together because they're very similar in nature. So these two benefits are fast convergence and aliasing, or as it's commonly known, load balancing. So let's start first with fast convergence. Bit of a tongue twister there. Now let's take it back to this server here. As we said on the last benefit, this is dual homed. It has a connection up to leaf 2 and it has a connection up to leaf 3. And this would build a link aggregation group where leaf 2 would advertise over to leaf 1 and leaf 3 would advertise over to leaf 1 as well via the spines. That to get to this server, you could do so via these leaves, via these actual sources. Now that sounds great, but here's a server. So this could be a bare metal server, it could be a hypervisor, and you could have hundreds or maybe even thousands of virtual machines actually running within that server. Now say this server wants to get initial connectivity, wants to send whatever packets out of this network, out of the leaves. So what it would do initially is it will send an ARP request saying, I want to get from this server here over to user 1. And it would send out an ARP request, and that ARP request would go, just for example, up to leaf 3 here. The source will basically decide which direction it will send that ARP request, either up to leaf 2 or leaf 3, depending on a hashing algorithm it does locally. Not going to go through that. But say, just for example, it picks leaf 3. Now at this point, what the leaf 3 does is it will update its MAC address table or its switching table to contain the server's MAC address in its source table. Now at this point, it will then advertise that over to leaf 1, but it also advertise it over to leaf 2. Now, because that advertisement has not come from leaf 2, because leaf 2 didn't get that ARP request, leaf 2 is not going to advertise to leaf 1, I've got that MAC address connected to me as well. So in that case, what leaf 1 is going to do is to get to the server here, it's going to send all packets for all those thousands or hundreds, whatever it is, through spine 1 or spine 2, but essentially all hitting this leaf here. So it's all going to hit leaf 3. That in itself is a problem. And it's a problem because what happens if this link goes down? Well, thankfully, because of the route type 1 that I described earlier, leaf 1 knows to get to that server, it can actually go through leaf 2. But we still don't want to use leaf 3 if that link then goes down. So this fast convergence is what's also known as a mass withdrawal. And what this means is that leaf 3 would advertise again a route type 1, but it would be set to a mass withdrawal, and it would contain all the MAC addresses and all the destinations that were previously advertised. So within here, say there was just 100 virtual machines and all their MAC addresses, leaf 3 would advertise over to leaf 1, to this source here, basically at the end of the day, to say, if you want to get to this server, you can no longer go through me because this link here is actually broken now, it's down. And at that point, leaf 1 would update its VTEP table to say, if I want to get to that server, I'm now going to use leaf 2. So that is what fast convergence basically is. It's the ability for that leaf to send a mass withdrawal message via the EVPN route type 1 to advertise to remote leaves, don't use me to get to this destination because that link in this example is now down. Fast convergence. But what is aliasing? Well, if we turn this on its head, if we look at the flip side here. So user 1, again, it doesn't know, does it, that it can go via this route here or via that route there to get to leaf 2 or leaf 3, essentially to get to this server. It doesn't know, and quite frankly, it doesn't care. It doesn't need to know. But leaf 1 needs to know, and leaf 1 cares about where it's going to route those packets from user 1 if it wanted to communicate to this server. And leaf 1 knows via the route type 1, the auto discovery ESI, the Ethernet segment identifier, that to get to this server, it can get to the server via VTEP 2, leaf 2, or via leaf 3. But what's interesting in the EVPN world is, recall when I said the server sent an ARP request up to leaf 3 and that this leaf then updated its MAC address table and then it sent the advertisement over to leaf 1. That's fine, that's great. That's actually what's known as a route type 2. And again, I'm not going to go into the packets, but just know the route type 2 in the EVPN world is basically an advertisement of the MAC address. So leaf 3 would advertise a route type 2 containing the server's MAC address and advertise that over to leaf 1. And at this point, leaf 1 then has the MAC address of the server as well as the Ethernet segment identifier, which has come from leaf 2 and leaf 3. But it's only got the MAC of the server from leaf 3. So at this point now, what's going to happen? Is leaf 1 going to send all packets over to leaf 3? Well, that wouldn't be ideal because at some point this device here is going to get overwhelmed and then it's just going to drop off the face of the planet. What I find really smart in the EVPN world is that leaf 1, it has that MAC address of the server via a route type 2, which has come from leaf 3. And it's also got the Ethernet segment identifier, which is the same, and that has come from leaf 2 and leaf 3. And because that Ethernet segment identifier, it's the same 10 hex value, leaf 1 just knows that if it wanted to get to this MAC address, it could actually use the VTEP tunnel which is built to go to that same Ethernet segment identifier. So if leaf 1 has a tunnel going to leaf 2, and let's just call this VTEP 100 just for simplicity, and it's got another VTEP tunnel going to leaf 3, and let's call this VTEP tunnel 200, it knows at this point that to get to that same destination, to that server, it can send packets over VTEP tunnel 100 and over VTEP tunnel 200 because of all the information it's got via these two route types. The route type 2, which has only come from leaf 3 because it was advertising the MAC address of the server itself, but because both leaf 2 and leaf 3 have advertised that same Ethernet segment identifier, the same 10 hex value, which advertises this link aggregation group, at this point, leaf 1 knows to get to that server, it can send packets to leaf 2 and across to leaf 3 via spine 1 or spine 2. Aliasing, load balancing. I don't know about you, but I find that very smart. We've only got one route type, the route type 1 from leaf 2, and we've got two route types from leaf 3. But leaf 1 knows, based on that 10 hex Ethernet segment identifier that's identified in route type 1, because it's identical from leaf 2 and leaf 3, it knows, and it almost assumes, and it does so rightly, that to get to that destination, to get to that server, it can do so via leaf 2 and leaf 3 because they're advertising that same Ethernet segment identifier, that same 10 hex value. So the third benefit, the third part I want to talk about in terms of benefits when it comes to EVPN technology, EVPN routing, is this point here, active forwarding, really more specifically designated forwarder or the designated forwarder. Now, we've already gone through active, which is when you've got a host, or in this case a server here, which is dual homed to, in this case, two different leaves, leaf 2 and leaf 3. And that's fine. You want that kind of resiliency. You want that kind of redundancy, of course. And on the last part, I talked about aliasing. Now, aliasing works really well. And in the last part, we talked about leaf 1 sending packets to the server, both via leaf 2 and leaf 3. So just for example, we'd go via this route here and over this route here, load balancing between them. Now that works really well for unicast packets. But however, there's another form of packets, and the acronym always makes me laugh. I'm a bit of a child like that, but that is broadcast, unknown unicast, and multicast traffic. And so I'm just going to write bum here because that is the acronym. That's what makes me a child and just giggle. Bum traffic. Apologies. But bum traffic. So the aliasing works really well for unicast packets, but it's not very well at handling bum traffic, whether it be broadcast, unknown unicast, or multicast traffic. But why is that? Well, let's look at it from first user one. So user one's going to send some form of bum traffic. Doesn't really matter what it is yet, whether it be some kind of OSPF adjacency, or it really doesn't matter, use your imagination. But user one wants to send that bum traffic to the server here, and the traffic goes up to leaf one. And as we know at that point, leaf one can send this traffic via spine 1 or spine 2. And because this server is multi-homed to leaf 2 and to leaf 3, leaf 1 can send that traffic via that VTEP, that VXLAN tunnel endpoint, to either leaf 2 or leaf 3. But here's the interesting scenario. When that bum traffic comes over to leaf 2 and comes over to leaf 3, that traffic, both from leaf 2 and leaf 3, is going to be sent down to the server. And as such, the server receives duplicate copies of that bum traffic because it's got the same traffic, that bum traffic coming from leaf 2 and coming from leaf 3. So that's not ideal. We've created duplicates, and bum traffic in itself is something you want to minimize as much as possible on any network. So there's that way in terms of coming from user 1 to the server via the spines, but the bum traffic then being almost duplicated and sent to that server via leaf 2, leaf 3. But what happens if the server then sends bum traffic? So let's say the server here, it again sends that bum traffic up to leaf 3. And let's just say, for example, that leaf 3 decides, and the destination is destined for user 1 here, which is in VLAN 10 VNI 5010. But leaf 3 decides it's going to send that bum traffic via spine 2 down to leaf 1. So leaf 3 would then send that traffic over the VTEP to leaf 1. But note the interesting thing here, user 2 is also in VLAN 10 and also in VNI 5010. And as such, leaf 3, it will also then, because it's bum traffic, send that traffic down or through leaf 2 via spine 2. And at this point then, it then also comes back to the server and down to user 2 as well. And see what we've done there, the server has sent that bum traffic up to leaf 3 and it's again come back down to leaf 2 and back to the server. So we've actually created a loop here. A loop is never great, whether it be layer 2 or layer 3. So we've got an issue where we're coming from user 1 to the server, and then we've got an issue when we're coming from the server to leaf 1. So we've got an issue in both directions, and this is where the designated forwarder is a huge benefit when it comes to EVPN. Now the designated forwarder allows split horizon rules to actually take place. So let's just say, for example, that leaf 3 becomes that designated forwarder. And if you're interested on what the designated forwarder is, I'm not going to go into too much detail too soon, but just know that we would be talking about the EVPN route type 4. So the route type 4 basically is an election process between two leaves or two access switches, if we're talking about enterprise networks, which are connected to the same multi-homed tenants, to the same multi-homed server in this case. Basically, leaf 3 and leaf 2 would decide amongst themselves who's going to be the designated forwarder for bum traffic for a given VLAN. So leaf 3 might be the designated forwarder for VLAN 10, whereas on the next election process, leaf 2 might be the designated forwarder for VLAN 11. And it goes round and around, it goes through a round robin decision-making process, and then leaf 3 would be the designated forwarder for VLAN 12, and then leaf 3 would be the designated forwarder for VLAN 13. You get the point. It's doing load balancing of traffic when it comes to bum traffic. But the concept of the designated forwarder is any bum traffic that comes from remote host has to go through the designated forwarder, and then the designated forwarder will forward that bump traffic down to that destination itself. So going back to the original concept, user 1 wanted to send bump traffic to the server here, and he actually sent that bump traffic to leaf 3 but also to leaf 2. Well, because leaf 2 is not the designated forwarder for VLAN 10, what would happen is leaf 2 would just simply drop that bump traffic. It would just drop those packets because it's not the designated forwarder for VLAN 10, whereas leaf 3 is the designated forwarder, and as such it will forward that bump traffic down to the server. But what about when the server sends bump traffic up to leaf 3, which happens in this case to be the designated forwarder? Well, the designated forwarder is still then going to send that bump traffic down or over to remote VTEPs that are in the same VNI with that same VLAN, but because leaf 2 also is interested in VLAN 10 VNI 5010 traffic, when that bump traffic comes down to leaf 2, because it is not the designated forwarder again for VLAN 10 for VNI 5010, it's going to drop that information. It's going to drop those packets right there. So this designated forwarder is absolutely superb when we start talking about bump traffic. We need the designated forwarder for bump traffic. Unicast traffic just works. We've got aliasing, we've got fast convergence or mass withdrawing, we've got multi-path. That works really, really well. It gives us redundancy, gives us load balancing, multi-path, etc. But we need that designated forwarder when it comes to bump traffic. And here are the fourth benefits when it comes to EVPN, Ethernet Virtual Private Network routing. I've really put these two benefits into one because they're kind of linked like the ones I've done previously. But first is talk about the minimization, the reduction on the flooding of the unknown unicast packets, which is one of those packets that falls within the BUM category, the broadcast unknown unicast and multicast traffic. So let's again look at it from the server here, which as we know by now is connected to both leaf 2 and leaf 3. It's a multi-homed device. So the server wants to send traffic to user 1 here. And as I've already discussed, it is going to then send a frame, a ARP request, because it doesn't know who is connected to leaf 3. It doesn't certainly know where user 1 is connected and all these spines, leaves, whatever it may be within the network. Now, before we actually start talking about what EVPN would do at this point, let's talk about what traditional Ethernet will do. Now, with traditional Ethernet, what the leaf or switch would actually do is it would, of course, update its MAC address table, saying the server is connected to me on port, whatever it is, gigi 001, 2, 3, etc. It doesn't matter. And it's the same in the EVPN world. That leaf device is still going to update its switching table, its MAC address table, to say this MAC address for this server is connected to this port. But in traditional Ethernet, what we're then going to do, what the technology does, is a flood and learn approach. And that's not really good because leaf 1 knows I am searching for the user 1. So it's then going to flood out of all connected ports. Have you got this MAC address? Have you got this MAC address? And these spines are going to forward that on. Have you got this MAC address? Have you got that MAC address? Have you got that MAC address? It's a flood and learn. And it takes some time then to learn where that MAC address is at layer 2, and that's assuming that it's in the same local area network. With EVPN, we're not doing this flood and learn. And that is because we are using a route type 2. It's one of the update messages within the EVPN world, route type 2, where we are actually advertising that MAC address of the server here. So with the EVPN route type 2, which is basically a BGP update message, leaf 3 would advertise to all remote VTEPs, to all remote devices, that this MAC address is connected to me, that this server here is connected to leaf 3. So then when user 1 wants to send traffic back to the server, because this is a user, this is a server, it might be some kind of TCP file sending, etc. When leaf 1 needs to send traffic back to leaf 3, it knows exactly, either via spine 1 or spine 2, doesn't matter, it knows to send that traffic back to leaf 3 because it has learned the server's MAC address is connected to leaf 3, and thus it's completely minimized the need to do flood and learn. It's completely removed it actually, and we've minimized the need, the transmission of the unknown unicast that typically you will always get more of in traditional Ethernet networks. Well, what about Proxy ARP? Well, the great thing about root type 2 is it will send a MAC address of the actual server here. So I'm just going to put a server here and on the top just root type 2. So that EVPN root type 2 for the server will contain a MAC address, but it will contain other fields as well. I'm not going to go into too much detail too soon, but optionally it will also contain the IP address of that server. And just as I just said, that root type 2 is advertised to all remote VTEPs that are interested in that same VNI, in that same virtual network identifier. So if user 1 wants to establish that TCP connection to the server, it will send an ARP request saying, you know, who is this IP address? What's the MAC address associated to it? And at this point, because leaf 1 has learned via that root type 2 from leaf 3 that the server is connected to me and it has this MAC and IP address, at this point leaf 1 is then going to do that proxy ARP down to user 1 and say, use this MAC address and use this IP address of the server. Brilliant. Proxy ARP, the ability for the leaves to respond locally to an ARP request when that destination is completely in a different network. That is just absolutely brilliant. So on these 2 points, minimization of unknown unicast, we've got rid of that flood and learn. We're using those VTEPs, we're using those leaf devices to advertise the MAC addresses that are locally connected to that device and advertise them to remote devices. And then in that root type 2, optionally, that leaf can snoop IP addresses and the associated MAC address and advertise that IP address to remote devices, allowing them to do a proxy ARP. And here's the 5th benefit when it comes to EVPN, Ethernet Virtual Private Network, and that is the distributed layer 3 gateway. Sounds quite complex. It's really not really, but do know when we're talking about distributed layer 3 gateways, we're actually referring to Anycast or Anycast gateways, which kind of gives away what this is. These gateways are Anycast. They're anywhere or anywhere you configure them to be. So let's use this example here, leaf 1, leaf 2, leaf 3, with the user 1, user 2 and the server respectively want to communicate to the internet. So I'm just going to try and draw the internet cloud here. Actually, that's not too bad. And the internet is connected to a firewall, ideally, which is connected to spine 1 and spine 2. So we need to configure the spines then to allow external connectivity and maybe for allowed hosts, allowed devices to connect to user 1, user 2 and the server, depending on use case, etc. Now, where does this distributed gateway, this Anycast gateway, come into it? Well, what you would do on spine 1 is you'd configure a virtual IP address. So if we look at the IP address for user 1, I've slightly drawn over it, but it's 10.1.1.1. User 2 is 10.1.1.2. Server is 10.1.1.3. So we want to configure that gateway, of course, to be within, just for example, that /24 network. So let's say the virtual IP address on spine 1 is 10.1.1.254. And on spine 2, we can then configure the same virtual IP address, the 10.1.1.254. Now, they're also going to have a virtual MAC address. I'm not going to draw it out, but just know there is a virtual MAC address which is pre-configured for you. It's actually the same MAC address that's used for VRRP. We're not doing VRRP here, this is EVPN, but it's the same MAC address. Now what this allows is it allows spine 1 to advertise down to leaf 1, down to leaf 2, across to leaf 3, and it allows spine 2 to advertise down to leaf 1, down to leaf 2, down to leaf 3. Now if your users, your user 1, user 2 and the server want to get to the internet, I am your gateway. I am your gateway, but that's obviously for spine 1 and for spine 2. So it allows you to distribute your gateways across your network. So if spine 2 was to fail for whatever reason, all those devices can still get to the internet in and out via spine 1. But of course there's then the question of the next hop. What are the leaf 1, and leaf 2 and leaf 3 going to use as their next hops? But because of course spine 1 and spine 2, they're going to have different IP addresses, not virtual IP addresses, but different IP addresses in terms of connectivity between the leaves. Well, in this case, what would happen is spine 1 would advertise its loopback 0.x interface. I say .x because it obviously depends on the network. So here, if we look at the network, it's VLAN 10, VLAN 10, VLAN 10. So that .x is actually going to be loopback 0.10. And likewise for spine 2, it's going to advertise its loopback 0.10. Now, each of these loopbacks are going to have their own IP address. So IP address of whatever it is. But that next hop is then advertised down from spine 1 to leaf 1, to leaf 2, to leaf 3. And spine 2 advertises that next hop, its loopback address, to leaf 1, to leaf 2, to leaf 3. And then these leaves know that if I want to get to the internet, my gateway is here, my gateway is here, but oh, hang on, I've got two physical as such next hops. I can go via this IP address here for spine 1, or I can go via this IP address here for spine 2. Multiple next hops, but going to the same virtual IP address with the same virtual MAC address, and thus you are distributing your gateway across your network. Now, a big point here is that you can actually decide, depending on your use case and the type of traffic you've got on your network, you can decide on where that that gateway is actually positioned. So if it's on the spines, as I've been detailing here, that would be referred to as CRB, or centrally routing and bridged. So that's where you've got your layer 3 gateway up on the spines, or if it's in the enterprise network, up in this case in the collapsed core, that distribution core layer. But you can also have the layer 3 at the leaf devices here. So on leaf 1, leaf 2, leaf 3, you can have that layer 3 gateway at the leaf devices, or if it's the enterprise network, down on the access devices themselves, depending on your architecture. Again, it does depend on the type of traffic you've got. If you've got more east to west traffic, or if you've got more north to south traffic. It really does depend on where you want to position those gateways. But again, this is a big benefit when it comes to EVPN. And there we go, everybody. That is the end of this episode. That is the end of part 2, where we've discussed about the benefits around EVPN, or Ethernet Virtual Private Networking. And as you can see, there's actually a lot to EVPN, and that's why there's a lot more parts that will come in this series. But EVPN brings with it a lot of benefits, such as the aliasing or load balancing, multi-path. The fact that EVPN is in itself carried by BGP, specifically MP BGP, is in itself a massive benefit, because BGP is so scalable and just really so powerful. And then when you add in the ability to have a designated forwarder to get around the BUM traffic, the broadcast, unknown unicast and multicast, and an active ability to multi-home tenants or servers like we did, and to use the underlay as well, EVPN then becomes a very capable, very efficient and very powerful routing mechanism for the overlay. So I hope you enjoyed this video. I hope you enjoyed this part. If you did, please subscribe to my channel. It's the best way for supporting my channel as it continues to grow. Any questions or comments, let me know down in the comments box. I really do enjoy hearing from you all. Other than that, thanks for watching and stay tuned for more.